All right, good morning, class. This is Construction Methods Learning Plan 8 discussion, lecture discussion here. All right, so here we go. So the purpose of this is to review density and soil compaction due to construction methods, because typically you're out there on site and running density tests, but also you should be observing how they're doing the density testing and how they're compacting, make sure you're placing it in lifts, and make sure you're using the right equipment. And then the second part of this is, how do we estimate how much needs to be placed or excavated, just for volumes, excavation volumes, is for estimation from, we can use that from our data that we obtain from soil borings, etc. Okay, soil, what is compaction? Remember, compaction is the process of applying energy to loose soil to consolidate it and remove voids. Some are the voids. So therefore, increasing the density, shear strength, and consequently its load-bearing capacity. This is why we need to compact soil. Okay, so here's some example of compaction equipment that we use on non-cohesive soils, which are gravel, sands, and silts. Okay, so this is a steel smooth drum plate roller. Okay, this is a little remote control walk behind here that we can use to compact here. Here's a this is a walk behind plate compactor. Okay, and this is a jumping jack. Okay, so when you're going to be watching these pieces of equipment as you're out there inspecting these projects, you're not just going to be sitting in a truck and just waiting to do your density tests. You want to watch them to make sure they're using this equipment correctly, or not, or we're not putting this jumping jack on top of the pipe or cracking the pipe, etc. Okay. So this is compaction equipment used for cohesive soils, clays. Okay. So we need these are called sheep's foot rollers. What we need here is we need to knead that clay together, just like when you remember when you're a young child playing with Play-Doh. How did you get that clay to turn into a uniform smooth ball? You kneaded it together with your fingers, and that's what this needs to do. This needs it, okay? So again, here's a manhole. See how tight this can get to? And I mentioned this over and over. It's very important that we get compaction tight, close up against the sides of the manholes, so we don't get any piping of soils, sediment, and manholes and stuff. Okay. Obviously, the soil is a little bit too wet here, huh? So you can see this machine is buried. So what we can do is, one, we have to dry this out, or we can increase the size of these compaction equipment, these sheep foots here. Okay, so this is cohesive soils. See, we're kind of kneading it together. All right, so when we're doing trenches, we're always putting in lifts. Here's a plate compactor attached to an excavator, doing a slope here. And yes, they do make these for backhoes, so we can actually compact cohesive soils. So make sure they're using the proper equipment. Okay, proper equipment. Sheep's foot for clays, plate compactor for all other. Okay, why is it important? During construction, soils is disturbed. Even though we're digging in a foundation, we're in a natural soil, there is still some disturbance there. So what we want to do is we want to make sure we compact it back into place. Okay. Before a soil can support a structure over it, it must be compacted and consolidated. Okay. All right, so what does soil compaction provide? It increases shear strength because the particles are close together and they're interlocking. Okay. It reduces settlement. Well, 'cause remember the weight volume relationships you did in soil mechanics and cement and ags. You have the void ratio is decreased. So how do we get soil sediment? Basically, if the particles are further apart, and also when we put a load on them, they want to push together. So that's what settlement is. Reduces swelling and shrinkage of soil. If we get those particles tight together, there's less room for water to be inside there. So as you know, what happens to water when it freezes? It expands. Okay, so if we can get less water in there, that'll help with that. Decreases permeability. We're creating by compacting, we're creating less channels for water to flow through that soil. Minimizes frost damage. These obviously are important here. I guess they go hand in hand. Frost damage, right? We compact it together, less water in there, less frost damage. Increases erosion resistance. Okay, so we need those particles touching, so there's friction, so when it rains it doesn't want to carry those particles around. Okay, key, erosion. All right, Proctor curve. So remember when we did this Proctor curve, remember we did it at various water contents. Okay, we increased the water contents from left to right. And then basically we wanted to see how much we can cram it into that mold. And then as the water contents came up, we call this the optimum density and the optimum water content. Just enough water to make that perfect sandcastle. Remember that perfect sandcastle. We don't want it too dry. We don't want it too wet. We want it just perfect. Okay. So density is also dependent on the compactive energy applied to the soil. Okay. So the bigger the machine, the bigger energy we can put in the soil, the more compaction we can get, the more density we can get. Okay. All right. So here's some different curves, basically water content. So the more energy, so if you look at the trend here, the more energy we put into there, okay, the higher the density. However, if you look at our optimum water contents, they decrease. Because what happens to materials when we put more energy? Just think of an earthquake. They're more sensitive to water. Okay. Okay. So typically the modified Proctor has a greater density and a lower optimum water content for a given soil. Because remember the standard Proctor, okay, here's the modified, okay. Remember the history is we started with a standard, but because over time traffic loads and equipment got heavier, so we increased to the modified, okay. So the standard, here's another curve here. So the standard is a 5.5 pound weight dropping 12 inches, and the modified is a 10 pound weight dropping 24 inches. So it's a lot more energy, which increases our density, but the water content goes down. All right, surface zone compaction, subgrade preparation. Prior to backfilling, check site recommendations. Make sure at the right elevation. You surveyed. They stripped the topsoil. We make sure we're in the right location. Okay. Geotech report. We can find this all in the Geotech report. Okay. Then we're going to, before we do any compaction, remember we're going to proof roll the natural subgrade with a heavy piece of construction equipment, such as a tandem axle truck. Okay. If we see permanent indentations, we're good. If we see it all of a sudden it starts deflecting, there's issues there. We got to dig that out and recompact it. Okay. So we want a loaded tandem axle truck, and you walk right next to it and watch it. Okay. So areas exhibiting excessive deflection or rutting should be trimmed and removed. So rutting, so we can have rutting, right? We want permanent rutting, but we don't want it too deep. If it's too deep, that means the underlying layers below 12 inches have not been compacted correctly. Because remember those nuclear density tests, they can only measure to a depth of 12 inches. That's it. So if you show up and they're done placing all the fill and you measure the top lift, that's all you're measuring is the top 12 inches. It doesn't mean they compacted the bottom, anything below 12 inches or deeper. Okay. All right, structural backfill. Any soil can be used as structural backfill with the exception of organic materials or other materials that can decompose or disintegrate. Okay, backfilling procedures. Materials should be spread in thin lifts, usually 6 to 12 inches, and compacted to required density. So obviously with a big machine here, we can go 24 inches, smaller walk behind plate compactors down to 6 inch. Okay, 6 to 24 inches. Okay, this is pushing it with this. Okay, so because this, when we're compacting it, we need to compact the whole thickness, not just the top, the whole thickness. So if we do a plate compactor across here, we're probably only reaching down 6, at the most 8. So this bottom is not getting compacted. Okay, lift thickness is depending on the soil type and the size of compaction. Okay, clay soils, cohesive soils, we need a little thinner lifts because we need to knead that. Okay, so jumping jack, walk behind plate, smooth drum. So, okay, different sizes, different lift thicknesses. This is right out of the book. This kind of shows different kinds, what we use to compact different thing. So here, this says sheep's foot for silt. Yes, that will work. Usually static rolling works for silt too, because silt is very sensitive to water, but a sheep's foot will work for that. But typically we see a sheep's foot using clay because our clays have silt in them. But a pure silt is very, very difficult to compact. All right, compacting cohesionless soils. Sands, gravels, and silt respond best to vibratory methods of compaction. Okay, keep in mind if we have a high water table, we're going to start liquefying the soil. So sometimes we have to turn off that that vibration. Cohesionless, sand, gravels, and silts. Cohesionless soils, plate compactors, jumping jacks, steel smooth drum. Okay, there we go. Steel smooth drum, jumping jack, plate combined. This is a remote control. Yeah, loaded earth movers. This is preferably because typically what happens if they don't vary their track. A lot of times we're going to see this being less compacted than where the wheels always run. So it works, but I don't prefer it. Okay, because you want uniform compaction across the whole site. Cohesive soils, clay, kneading methods of compaction. Kneading. Okay, sheep's foot, non-vibratory rollers. Okay, I don't need any vibration. We need to knead it. Sheep's foot. There we go. Okay. Okay, so sorry about that call interruption there. So again, cohesive soils using a sheep's foot roller to knead the compaction together. So from current slide, there we go. All right, what do we do if we can't get compaction? Is the subgrade deflecting either loose or compressing? So that's when we do that proof roll. You got to make a decision. Do you see water on the surface? Do you see it like pumping up water when a truck runs over it? That means there's some underlying issues. We can also use that DCP device and hand augers to just do some investigation to see where that problem is, so we can kind of target where that zone is, what depth that zone is. Hand auger out, say, we could be as deep as 4 or 5 feet, and you hand auger out, and all of a sudden you find an organic layer, or you find some really wet soil underneath, especially cohesive soils. Say it rains one day and they come back the next day and they bury it. So that's going to eventually pump up to the surface. So we got to just do investigation techniques. Okay. If yes, we need to remove the backfill and prepare subgrade properly. Okay. Well, and if the contract says that you have to test every lift, and all of a sudden you're not there to test every lift, and they didn't call you, they're going to have to dig that all out and do it over again. Okay. All right, if the material is too wet, so we have 3 options. Is the material too wet, too dry, or there is not enough effort applied? So this is when we know the subgrade is fine, the underlying, we don't see any deflection, okay? All right, so if the material is too wet, we disc it or scarify it, allow it to dry to an acceptable water content range. So remember that optimum water content of that Proctor curve. Remember, we usually want to stay within plus or minus 2% of that. We allow it to dry, recompact it, and retest. Okay? If it's too wet, we got to dry it out somehow. Okay? If it's too dry, we're going to disc it. We're going to add water. Okay? And then we're going to mix it again with the water and then recompact it and retest. Okay, it doesn't do any good just to add water and let it sit there without scarifying it or mixing it up. It needs to be mixed up so all the grains are uniform. Okay. All right, what to do if we can't get compaction? If it's in a material water content range, proper range, plus or minus 2%, basically you just need to put more effort in there. Okay. Important. Subsequent lifts of soil should never be placed over soil that is not properly compacted and tested. All right. Now, on to the next thing. So, let's talk about earthwork. Let's talk about moving things here. Okay? All right. So, if you look at the natural soil conditions of our soil. So, just give me a second here. Okay, so if we look at the natural state of soil in its natural condition, remember this is a phase diagram. We have solids, water, air. Okay, so I want you to look. So as we go through all of these stages, the solids, the volume of solids does not change. Okay, so if we were in a natural condition called bank, they call this bank. If we excavate it, what happens? The water change, but the air, the volume of air changes, right? Okay. And then what happens if we have to moisture condition it? So the solid stays the same. So if we add water, if we put a hose to it, some of those air voids are now becoming filled with water. So the volume of air goes down, but the volume of water goes up. Because remember, air plus water equals volume of voids. Okay? And then once we compact it back, okay, now what are we reducing? We're reducing the void ratio. We're reducing the volume of air. Okay, but the water is staying the same. Okay, so this is important that you understand these three phases of, or the phases of how soil is. So this is called bank condition. This is called the compacted condition. This is the hull. Okay, all right. All right, so there we go. All right, so for an example, if we have a bank, a volume of 1 cubic yard, we excavate it, all of a sudden it turns to be 1.25. They call that the loose condition. Okay. Then we compact it to 95% of the modified Proctor. Okay. And all of a sudden our volume is actually 0.80 cubic yards. So we actually lose volume by compacting it from the natural state. So I want you to, so there's bank, loose, compacted. Okay. So here we go. We dig it out. We haul it. And then we compact it. So another example. Okay. It becomes, so we're losing 10% of the volume on this example. We're losing 10% of the volume from when we excavate it, but we're gaining 25% volume when we're hauling it. So you just understand that relationship. Okay. So you need to, reason why you need to understand this, because you can't just estimate amount of excavation or amount of fill based on volumes from your drawings, your, I guess what I'm trying to say, your cut and fills from your drawings that you do. Okay. I call that paper volume. Okay. Because you got to realize that it gets bigger and then it gets smaller. Okay. All right. So shrinkage. So they call these shrinkage and swell factors. Okay. So the swell factors from when they go. So if we go back, a swell factor from bank condition to transport condition. So it swells up. Okay. And then once it goes from loose condition down to the compacted, there's a shrinkage factor. Okay. All right. So we are always comparing it back to the bank volume. Okay. Always back to the bank volume. All right. Bank, material in its natural state before disturbance. Loose, material that has been excavated or loaded. Compacted, material after compaction. Okay. Swell, percentage. Weight of bank volume divided by weight of loose volume. -1 times 100. Okay. Shrinkage, weight of bank volume. You notice the numerators in here. It's always related to the bank volume. Undisturbed volume, always to the undisturbed volume. Over weighted compacted volume. Okay. 1 minus times 100 will give us our shrinkage factor. Okay. So these two formulas are very important. All right. So we'll be using these. All right, so we ready? Let's do some example problems. So what I have here is I have these attached in Blackboard, and then we'll quickly go over your homework, and then this lecture will be done. So example 1. Undisturbed samples were obtained from boring logs in a proposed cut area. The samples had an average dry density of 108 pounds per cubic foot and an average water content of 9.1%. A Proctor test was performed on a representative sample and produced on a maximum dry density of 124 pounds per cubic foot, and an optimal moisture content of 12.8%. Okay, so already I know to get to the optimum, I have to go from 9.1% to 12.8%. So I got to add water to get it closer. Okay, a loose volume dry density of 90 pounds per cubic foot was estimated. Okay, the proposed grading plan calls for 12,000 cubic yards of cut and 11,000 cubic yards of fill. The specifications call for relative compaction of 90% of the maximum dry density. Okay. All right. So how do we get these weights? A way we can actually weigh this is actually figure out the volume of the inside of a box of a truck, weigh it empty, dump the material in there, level it off, and then weigh the truck again. And knowing the volume of that box of the truck, we can get an estimated weight. Okay, I've done that before. Or we can use from, if it's cohesive soil, we can use it from Shelby tubes, getting unit weights. Okay. All right. So 1, compute the swell factor and calculate how many cubic yards of fill will have to be hauled from the cut. Okay. So according to the plan, when you do your Civil 3D plan, you got to do 12,000 cubic yards of cut. Okay. So let me go find my examples. All right. So we need a swell factor, right? So let me, what's going on here? There we go. This is the one I want. All right. Swell factor. All right. Compute the swell factor. All right. So if I look at the formula here, bank volume divided by loose volume minus 1. Okay. So bank volume, okay, the samples had an average dry density of 108 pounds per cubic foot. Okay, there's 108 divided by our loose volume, okay, undisturbed samples, minus 1 times 100. So I have a 20% swell factor, okay? All right, so 12,000 cubic yards times 1.20 equals 14,400 cubic yards to haul, okay? All right, so that's number 1. So you notice I put the 1.20, so I can take 12,000 pounds times 0.20, 12,000 pounds times 0.20, and that's 2,400 pounds. So that's 20% of 12,000, or I'm sorry, 12,000 cubic yards. That's 20% of 12,000 cubic yards. So, and 20% of 12,000 cubic yards is 2,400 cubic yards. So I just add that back to the 12,000, and I get 14,400. So I'm basically what I'm doing that by putting the 1 in front of there. Okay, 1.20. Okay, that's different ways to do this problem. So that's number 1. So I got to haul 14,400 cubic yards. Okay. All right, problem 2. Compute the weight of the soil in tons of fill soil from the cut based upon the average water content. Okay, total weight equals weight of solids, bank volume times 1 plus water content over 100. All right, so if we know our dry density is 108 pounds per cubic foot, that's our bank volume, times our natural water content, we know 117.8 pounds per cubic foot is our wet density, okay? So 117.8 pounds per cubic foot times 27 cubic feet per cubic yard, okay, times 12,000 cubic yards. So remember, we're always going back to bank volume, okay? Go to bank volume. Air weight equals 0 times 1 ton equals 2,000 pounds. So basically, I'm going to haul out 19,083.6 tons. Okay. So basically, knowing the water content, so I should have delivery tickets based on tonnage, right? You be able to look at slips. I should add to this about there. Okay. So remember, we're always measuring our calculations from bank volume. Okay, because this is what was in place, and that's the moisture content is in place moisture content, not loose volume. Okay, so that's number 2. Number 3, compute the shrinkage factor and calculate how many cubic yards of fill are required for the fill area. All right, so we know to go 11,500 cubic yards of fill. Okay. All right, so shrinkage factor, 1 minus bank volume divided by compacted volume. Okay. Bank volume, again, is 108 pounds per cubic foot. Compacted volume. So remember, in the problem it says we're going to compact it to 90% maximum dry density. Our maximum dry density is 124 pounds per cubic foot. Okay, so based on percent compaction. So I know I'm going to compact that to 111.6 pounds per cubic foot. That's 90% of my maximum density. Okay, now knowing that, my shrinkage factor is 3.2%. So I'm losing 3.2% volume of 12,000. Okay, so 11,000. So now I don't want to add that. I'm losing that, right? Okay. So 11,000 cubic yard times 0.032, so basically 3.2%, that's 368 cubic yards. So if I add that to that, I need 11,868 cubic yards. Okay? Or if I just put that 1 in front of there, 11,000, I get the same answer. So see the difference? This calculation is doing this in one step. Okay? All right, so that's my shrinkage factor. So we need to haul in 11,868 cubic yards. Okay. Number 4, compute the import or export of fill is required based on the cut volume in the cubic yards. Okay, so our cut volume is 12,000 cubic yards. That's in place, paper, minus, this is what we're going to compact it to. So we're going to have to haul out 132 cubic yards of excess. Okay. All right. And number 5, compute the quantity of water in gallons, 8.34 pounds per gallon to bring the fill soils to optimum water content or moisture content. Okay. All right. Number 5. So my gamma D at 90% is 111.6 pounds per cubic foot, 90% of my maximum dry density according to the Proctor. Okay. All right. So weight of solids of fill equals my dry unit weight, okay, times my volume of fill, okay. So 116 pounds per cubic foot times 27 cubic feet per cubic yard equal times 11,500 cubic yards of fill. So remember, we're always going back to the paper volume, okay. So weight of water equals the change in water over weight times the weight of solids. All right. So my natural water content is 9.1% from the problem, okay? But I need to get it up to 12.8%, okay? All right. So I'm going to take 34,651,800 pounds of fill, right? Because I calculated the weight of solids, and figure out how much my weight of water I need, okay? Which is 1,282,117 pounds, okay? Now knowing the volume of water equals the weight of water divided by the density of water, but I'm using pounds per gallon instead of 62 pounds per cubic foot. This is equivalent. So I need to bring in 153,731 gallons. Okay. So if you kind of look here, change in water content times the weight of solids. Okay. Or I did it a different way. Okay, natural wet weight at natural water content is 121.8. Natural at optimum, here's optimum is 125.9. Okay, so the weight of water, the difference is 4.1 pounds per cubic foot. Okay, 4.1 pounds per cubic foot, convert it, times 11,500 is 1,273,050. And I go back to this equation, 152,643. So So this difference is due to rounding. So either way, I get the same answer. Okay. All right. So that's that guy. All right. Example 2. Excuse me. A contractor needs to excavate 75,000 cubic yards of silty clay and haul it with a Caterpillar 690C dump trucks. Each truck can carry 27 cubic yards of soil per load and operates on a 30-minute cycle. So a 30-minute cycle means it picks up, it dumps, it comes back. Okay. Job must be completed in 6 working days with the trucks working 2 10-hour shifts per day. Using a swell factor of 25%, how many trucks will be required to get it done in 6 working days? Okay, how many trucks? All right, let's go back to the example. All right, example 2. All right, so they need to have a haul 75 cubic yards of bank volume. I have a swell factor of 25%. So they got to haul 92,750 cubic yards to haul. Okay, 2 10-hour shifts. Okay, so basically they're hauling 20 hours per day. They have 6 days to complete it, right? So if they're hauling 20 hours per day and they have 6 days to complete it, the days cancel out. I have to complete it in 120 hours. That's how much time I have to haul 93,750 cubic yards. Okay, each truck can haul 2 loads per hour, right? A 30-minute load cycle. Okay. Okay, does that make sense? Because a 30-minute road cycle, they can haul 2 loads per hour going there and back. All right, so each truck can haul 27 cubic yards per load, so the loads cancel out. So that equals 54 cubic yards per hour per truck. Okay, so each truck can haul 54 cubic yards per hour. All right, so if I need to haul a total of 93,750 cubic yards in 120 hours, okay, that means to complete that in 100, I need to haul 781.25 cubic yards per hour. Okay, now knowing that, okay, 781.25 cubic yards per hour divided by each truck can haul 54 cubic yards per hour. Okay, so per hour, I get 14 and a half trucks. So obviously I can't haul a half a truck, so I need 15 trucks. Okay, so that is that example. Okay, so with that, that is the examples about compaction. Okay, all right, so as soon as okay, so let me go back. So if you look here, I gave you this to help you with your assignment. Okay. And then here is your assignment, 1 through 6. Okay. If you're struggling with it, you got to reach out to me. Okay. Remember at 1:30 to 3 on Mondays is you can reach out to me to help me with this, to help you with this homework. Okay. So there's that. So what I just talked about was right here, and here's the solutions. Okay, so that's the end of this video. Thank you for your time. I'm always welcome to feedback how I'm doing this. This is the first time for all of us, so hopefully you understand what I was doing. I'm trying to learn to slow down and follow my calculations, so please, feedback is always welcome. Thank you.